Hello, my name is Miriama Jánošová, and today we will talk about organizing similarity spaces using metric halves. In this presentation, we will first define the metric half representation, then we will continue with our proposal of the MH3. Later, we will describe the experiments and provide the definitions of nodes ordering to showcase the viability of our proposal. And lastly, we conclude the presentation. The half representation of some group of objects, C, is defined as a set of boundary objects selected from it, such that every other object from C is covered by these boundary objects. Such boundary objects are referred to as hull objects. In the picture, you can see that the hull provides a tighter enclosing of the group C compared to ball representation, exploiting a medoid and a covering radius. For a metric hull to be useful, it is necessary to define a test that decides whether a new object is covered or not. Let us have some hull representation H that consists of objects P1 to PH, and then some other object O from the database. Assume that P and N is the nearest hull object of H to O. We say that object O is covered by the hull representation H if and only if the sum of distances between O and the remaining hull objects, while omitting the P and N, is smaller than the sum of distances between P and N and the remaining hull objects. In this paper, we proposed the MH3, which is a hierarchical n-ary tree index structure. As you can see in the illustration, the tree is composed of two types of nodes, specifically the leaf nodes and internal nodes. Objects are stored in buckets of leaf nodes. The internal nodes contain a list of pointers to child nodes together with their hull representations. In the following algorithms, we assume the bucket capacity to be C and the arity of the tree to be equal to A. We propose creating the MH3 by the bulk loading procedure, which builds the MH3 in a bottom-up manner. Firstly, we group all the database objects into leaf nodes, where each leaf node would contain C objects at maximum. Next, we apply the merging procedure to collapse all the leaves into the first layer of internal nodes, such that each of these internal nodes would have A children. The merging procedure is repeated until only a single node is obtained, which then becomes the root of the tree. To form a leaf node, we start by selecting the furthest object OF from the database. Such an object then becomes the new cluster's nucleus. Subsequently, until the capacity of the leaf node is saturated, we form a candidate set of the closest yet not clustered data by executing 1NN queries for each cluster object. We select the object from the candidate set whose sum of distances to the cluster is the smallest to become a part of the cluster. In the image that we provide on the slide, the object OC2 is selected. The motivation behind such leaf node computation is just to create compact clusters for the data with outliers, such that we would minimize the overlaps. Lastly, we compute the hull representation of the leaf from the objects in the bucket. And this procedure is repeated until all the database objects are processed. The next bulk loading stage is the merging procedure, which basically produces a new level of internal nodes and is repeated until only a root node is obtained. First, we select the furthest node NF from the previously established layer and execute a nearest neighbors query to gather a nearest nodes to NF. These nodes form a new internal node. Next, we compute the Hall representation of the new node while utilizing only the Hall representations of the children. To determine the proximity of nodes during the search, we measure the distance between Halls as the minimal distance between their Hall points. Searching in the MH3 for the nearest neighbors is done by a common procedure employing a priority queue PQ of nodes to be processed. However, the algorithm here gives only approximate results because we assume a limit on the number of visited objects during the search and also the manner in which the MH3 is built introduces some imprecision. The tree traversal starts in the root and nodes are visited based on their likelihood of containing relevant answers. Such a likelihood is determined by rank, and we define the rank exclusively based on the distances to the Hall objects, and the proper definitions of the rank functions will be introduced in the experimental evaluation. During the search, when an internal node is visited, we add its children to the priority queue, and when a leaf node is visited, we take objects from the bucket and update the answer. The traversal is terminated after visiting the limited amount of nodes. We performed experiments over the Profimedia dataset. It is a collection of 4,096 dimensional vectors extracted from photostock images by convolutional neural networks. We used two different sizes of data, specifically 10,000 and 100,000 images. We measure the similarity between the data by the Euclidean distance. To obtain the results, we employ an approximate k-NN search with increasing termination in 5% steps up to 100% visited objects. Subsequently, we measure the trade-off between the accuracy and the efficiency of a random object search, denoted as a recall. It is computed as a ratio between the number of correctly identified nearest neighbors that would be part of a precise k-NN search by a sequential scan and the number of the nearest neighbors to be retrieved. We compare the results with M3 optimized by the slimmed-down insertion. We analyze the way of ordering leaf nodes by comparing their Halls to the query object. The most encouraging ranking uses only the distance between the query and the closest Hall object. We evaluate the ranking on a shallow tree configuration that is composed of only a root node that directly references all the leaf nodes. The graphs on the slide provide a comparison between the recall of MH3 and M3 for varying number of visited objects in 1NN and 50NN queries. In case of the 1NN query, the performance of both index structures is more or less the same. However, the 50NN query reveals a significant improvement in the MH3 score compared to M3. Notice that MH3 reaches over 80% recall while visiting only the 20% of the database. To efficiently traverse the MH3 structure, we need to determine the best ranking strategy with respect to both leaf and the internal nodes. Employing the same ranking of internal nodes as we used for the leaf nodes, however resulted in a poor performance. Therefore, the ordering here needs to be more sophisticated. In the slide, we provide the most promising rank function. The covered condition provides a better ordering of halves that contain the query object, so halves with Q more to their center are preferred. For the 1NN queries, it is more convenient to prefer halves that are closer in overall, so the furthest half object is used. Whereas the nearest one was the best performing for larger K. Notice that the MH3 significantly outperforms the M3, especially in the 50NN query, where the MH3 already reaches over 75% recall when visiting only 20% of the database, compared to only 30% recall of the M3. The experiments prove that the node navigation by the rank function is rather robust. Lastly, I present selected results on the larger 100,000 images dataset. We set the structure parameters of both trees to obtain similar ones. They are summarized here in the table. Especially notice the fat factor of the MH3 that is lower by 1 magnitude compared to M3, which suggests a high compactness of the HAL representation. Figures in the slide showcase the details of performance of various KNN queries, where an approximation parameter has been fixed to visiting 10% and 20% of the dataset, respectively. Notice that the recall of M3 deteriorates with increasing K. On the other hand, the MH3's recall is more steady. The results manifest that the MH3 is able to outperform the M3 even on larger dataset significantly. So to sum it all up, the MH3 is a novel index structure based on the concept of metric halves. The low fat factor compared to M3 suggests a pronounced compactness. The experiments that we have performed manifest that MH3 significantly outperforms the M3 while visiting fewer nodes. Specifically, the MH3 achieves around 20 to 30% high recall on average on a smaller data, and 30 to 40% high recall even on a larger data set. Lastly, in the paper, we also outlined how an insertion of a new object into the tree would unfold. Note that we allow overfilling of the buckets since fuller nodes are advantageous in the case of splits. In the future work, we would focus on generating halves with more HAL objects in order to keep the representation even tighter, which may lead to further improvement of the approximate search. Furthermore, we would formulate other major ranking strategies to obtain a finer-grained tree traversal. Next, we would perform some more experiments to compare the MH3 with other well-known index structures. And lastly, we would optimize the code to reduce the building costs. That's all from my side, and thank you for your attention.